and also for your invitation and for organizing this wonderful and very important conference. Well, you will wonder why a physician holds a lecture at this conference about the programming language Pascal. And I hope you will understand it at the end of my lecture that Pascal has a lot to do with my career, with my work, and also with the work of the hospital department, which I am head of. And we are currently developing a new form of endocrinology. Endocrinology is a field of medicine which deals with hormones, hormonal disorders, and physiology of hormones. And this field is currently undergoing a transformation to a new kind of a field called systems endocrinology. And computer simulations and calculations are very important. And I will show you why Pascal is the optimal language for this. It spans a history of about 30 years of my own work, and I will begin with the medical needs, with the medical problems we currently have. Then I will show you the way how to solve these problems with mathematical models, and at the end I will show you how computer programming with Pascal can help to address these questions. And at the very end, I will show you some unpublished work, very recent work which we make, which stretches the boundary further. So, to begin with endocrine conditions, they are common diseases in the world, and to begin with thyroid diseases, diseases of the thyroid gland affect more than 10% of the inhabitants in developed countries. These are the numbers for the United States. And they have very important personal implications for the affected subjects. And the other big disease in endocrinology is diabetes, which also affects more than 10% of the subjects in the developed countries. And as you see here, the numbers are rising worldwide. So it is important to address these diseases. And this came into the consciousness of the public in 1945 when Franklin D. Roosevelt died a few days before the end of the Second World War. And he died of a severe stroke. And his successor, Harry Truman, initiated a program, the so-called Framingham study, which is still which is still active in the United States. And this Framingham study tried to answer the questions: which are the reasons for severe cardiovascular diseases, stroke, heart diseases, and so on. And what they found is that there are several factors which increase the risk. And these are hypertension, diabetes, elevated blood lipids, smoking, and a bit obesity. But one of the most important one is diabetes, which doubles the risk for suffering from heart attacks or stroke. And if it is combined with other risk factors, then it is even more increasing. And now from Framingham, we move to Rotterdam in the Netherlands. They also made an important study, and they prospectively investigated 10,000 inhabitants for over 10 years. And what they found is that thyroid hormones are important predictors of mortality, of sudden cardiac death. And this is the thyroid hormone 3T4, 3-thyroxine, and it significantly increases the risk for sudden cardiac death, even within its reference range. This is the normal range for 3T4, and subjects which are high in the reference have a nearly 4 times as high risks than subjects who are low. So these are very important conditions, and we ourselves could confirm this with a meta-analysis which we recently published, and we could show that both the controlling hormone TSH and the thyroid hormone 3T4 predict cardiovascular mortality and also subclinical thyroid disorders, so very light forms, are associated with significantly increased risk for sudden cardiac death. So what are the challenges now for endocrinology? They are to make a correct diagnosis of diseases, to address the short-term risks. Is not what we talked about this currently. A short-term risk is the risk of diabetic ketoacidosis, for example, or thyroid storms, but also to address the long-term risks, which we talked about. Then to reduce the risk of recurrence in subjects with endocrine cancer, and of course to improve the quality of life of affected persons. And all these questions can be addressed if we improve our understanding of endocrine feedback loops. They are in the center, and nearly every hormone in the organism is controlled by feedback loops, which enable the possibility to stay the hormone to be constant or to meet the requirements. And this is an example for adrenal gland, which produces important stress hormones. These are the gonads, which produce sex hormones, to only answer two questions. And what is this for? Well, in an environment which may be adverse and which may propose an organism with a lack in energy, with stress, with extreme temperatures and so on, it is very important to keep key physiological parameters in range. And one of the first ones who acknowledged this was Claude Bernard in the middle of the 19th century, who stressed the term the fixité du milieu intérieur, the constancy of the internal milieu of the organism, as the main goal of physiological regulation. And in the 30s, Walter P. Cannon coined the term homeostasis for this. Homeostasis means that the key property of the body remains constant. Temperature, concentration of hormones, concentration of metabolites, blood pressure, and so on. They are actively controlled constant by feedback loops. But today we extend these ideas because we see it is not always constancy. Sometimes the physiological variables have to be adapted to the needs, and this is now the term of allostasis, stability through change, but change towards a preset goal. So this is important for the adrenal gland. It is controlled by a control hormone ACTH, produce cortisol, and this inhibits again the ACTH secretion, and so we get patterns, circadian patterns with pulsatile release and also adaptability to stress. This is another more complex feedback loop for thyroid homeostasis, thyroid hormones, which are controlled, and of course blood glucose. The beta cells produce insulin, which lowers the blood glucose, and blood glucose stimulates the insulin secretion. And if this fails, if the beta cells go down, for example, through an autoimmune process, and type 1 diabetes results. And if beta cells work, but insulin doesn't work due to resistance, then type 2 diabetes evolves. And many other conditions, for example, COVID, we could recently show that feedback loops are very important in the pathophysiology of COVID-19. And nearly every field of medicine is affected by this. So how can we improve our understanding? And one way to make this is mathematical modeling of feedback loops. And the traditional way to do this are LT1 systems, LTI, for linear time invariant system. So we have here a feedback loop, we have a controller here, and we have here some gains, we have here load, which is injected, and here we have the feedback, and here we have a set point, which the feedback loop tries to approach. And then we can replace these blocks here by equations. And so we can calculate the development of the system over time here. This is a recursive equation because y of t is on both sides of the equation. This can be used for computer simulations, for example. But we can also solve these equations to get the steady state solution when the time goes to infinite. And this is the solution for a linear time invariant system. And of note, the relationships are linear. So the output of this element is G times the input, and it is independent of the location. The slope is always the same. This is also the case for inhibiting relationships, and these are also linear in this form of model. And one of these models was the thyroid model by Berman in 1961. Monius Berman, made extensive computer simulations with his IBM 704 computer, very large system with vacuum tubes, and he programmed it in Fortran, and so he made some simulations which are still important today because we learned a lot about the kinetics of iodine and thyroid hormones by this research. Another of these earliest models is this by Victor Bowley, who tried to model insulin glucose homeostasis and to understand diabetes a bit more. He used an analog computer with these kind of amplifiers to make these simulations. So these are the equations of the Bowley model. So the rate of change of insulin depends on of glucose here depends on glucose itself and on the insulin concentration and to external inputs. And very similar equation we have for insulin, with the exception that glucose stimulates insulin secretion, whereas insulin reduces the blood glucose concentration. But what are the problems of these early forms of models? One is seen here. If you have already a very low blood glucose concentration, and then the subject receives an insulin pulse, then from this model a negative concentration of glucose would result, which is of course impossible. So we have, it is important to improve the models. We have many other reasons, of course, too. And what are ways of improvement? One way is to address physiological parameters. So if an endocrine organ produces a hormone, then this is a rate, this is an amount of a substance over time. And this rate is then translated via a zinc, via distribution and elimination processes to a concentration in the blood. And how can we mathematically formulate this? By 4 building bricks: one for elimination and distribution, one for non-competitive inhibition, one for Michaelis-Menten kinetics, and one for plasma protein binding. Let's begin with elimination and distribution. For this, we have designed a basic building brick, which we call Asia element, for analog signal memory with intrinsic adjustment. And so we have a metabolite, Y of T, and its production depends on an input parameter. This is integrated, so the integral of this change of rate provides a concentration, but this is also fed back to the system itself and inhibits, again, its concentration. You can understand this by degradation of the substance, which depends on the concentration. And so we get this exponential equation which describes the evolution over time. But we can also solve this equation for the steady state behavior. This is alpha x divided by beta. And we can solve it for oscillatory inputs in the frequency domain. The next building brick important are Michaelis-Menten kinetics. So if an organ, an endocrine organ, is stimulated, it can't produce an infinite amount of hormone or metabolites or whatever. If the input signal gets higher, then the production nears a saturation level. And so this linear model is quite unrealistic, and we have to replace it by a nonlinear model, and we can derive it from the basic chemical reactions. So we have here an enzyme and a substrate, E and A, which form a complex with a rate constant K1, and this complex can dissociate it either to the initial substances again, to the enzyme and the substrate with K minus 1, or to the enzyme and the product to K2, and the enzyme gets recycled. And we can model this very simple mathematically by this Michaelis-Menten equation, y equals g times x divided by d plus x, where g is the maximum production rate which is possible for this enzyme or organ or whatever we have, and d is a half maximum constant, that is z input, which defined the half maximum output. So with these two parameters we have defined the shape of this nonlinear function. And we can not only use it for enzyme kinetics, but also for receptor binding and other important biological relationships. And we have defined this building brick, which we can use for modeling and simulation. The next step is non-competitive inhibition. This is the negative side, where we want to avoid this negative output if the input is very large, and we can arrive at this by a more complex equation, where we have also an inhibitor in this chemical reactions, and the equation is here, y equals g divided by 1 plus Lx. This delivers this nonlinear form where we never get a negative input. And of course, we can combine stimulatory and inhibitory inputs to get this MIME no CODI element, MIME for Michaelis-Menten kinetics, and no CODI for non-competitive divisive inhibition. And these elements, we can see here the stimulation via nonlinear stimulating input, and inhibition, the nonlinear inhibition by the inhibitor. And so the last element which we need is plasma protein binding. Many hormones bind to plasma proteins, for example, thyroid hormones, adrenal hormones, and we have to address this as well if you want to simulate a feedback loop. And this is a very simple, small feedback loop on its own. We have here the association constants K41 and K42 and the concentrations of binding proteins, and so we get the concentrations of the free hormone at the end, which is defined by the total hormone and the concentrations and the binding constants of the binding proteins. So putting this together to a feedback loop and modeling this requires a few steps. So we have the Michaelis-Menten kinetic of the feed-forward path. We have to address the non-competitive inhibition of the feedback path, and we have to combine the two parts with linear elements, with linear gains. And then we can formulate this with a recursive equation here. This recursive equation describes the development of the system over time. And what we can also do is we can solve this for the equifinal behavior in the steady state. If we combine some of these parameters to 3 variables A, B, and Z, then we get this quadratic equation for this simple feedback loop, which describes the behavior in the steady state. Of course, feedback loops may be more complex than this simple example. For example, we can have several Michaelis-Menten kinetics in series, but it is not a problem. If you have Michaelis-Menten kinetics in series, we can summarize them by defining a new meta-element which contains its variables, and so we have again a Michaelis-Menten kinetics for the response variable, and so we can use the same formalism to solve the equations. It is more complicated if the Michaelis-Menten kinetics are in parallel, for example with this feedback loop, which has two parallel pathways. Generally, we get to algebraic equations with the order m, which is k plus 1. K is the number of parallel loops here in the system, and the order of the equation, which describes this is m equals k plus 1. We all know that we can only solve equations to a maximum of grade 4, so we are limited to 3 feedback loops if we want to mathematically solve this nonlinear system. What if the system is more complicated? And what if we want to learn more about the temporal evolution and disturbing factors? Then we need more. Then we need more than mathematics. Then we need computer simulations. And for this purpose, we have developed a class library which we call CyberUnits bricks to be more specific. And this CyberUnits bricks library is written for Object Pascal, and it supports the simulation of the system both in the time domain and in the frequency domain. And it contains a lot of classes. The basic class is here the T-block class. You see here constructors, destructors, and more importantly, the simulate method and the frequency response property, which delivers the respective information. And this is a hierarchy of the class library, so nearly everything is defined, derived from the T-block class. And we have several building blocks, for example, a block for a proportional element here, and a first order time element here, and a dead time element here. These are the simple blocks. Here are invertible blocks, which can have both positive and negative inputs. For example, an adder element or a multiplier. They are invertible. And here in the life blocks unit, we have defined some classes for building bricks which are only important in life sciences, like Michaelis-Menten kinetics, which you learned, Asia elements and no-Cody elements. These here are visual classes. They are not important for the simulation itself, but if you want to draw the feedback loop on the screen or for printout, thank you, then these visual classes are helpful. So we can, for example, this is a very simple demo of these visual classes, and we can draw block diagrams with object-oriented programming in Pascal. This is a very simple example of a feedback loop created with CyberUnits. I will later make a demonstration of this, how easy it is in the afternoon. And so we can simulate the evolution over time. We get here a time series over time. We can plot it and we can visualize this, and this is the prediction of the system with the equations. We have used it, oh, it's so fast. We have used it for several feedback loops. This is an example for insulin glucose homeostasis. This is for the adrenal gland. And most importantly, and this covers also most of my own scientific life, is thyroid homeostasis. And for this purpose, we developed a computer program. Its development began nearly 30 years ago in 1994 in Zinc Pascal on this Mac SE. We also learned about Zinc Pascal this morning. This was an old object-oriented Pascal dialect. That's still old objects, so the old variant of Object Pascal. And but this software continued to evolve until today. This is a modern variant of SimTur, a program which simulates the thyroid gland with many evolutionary steps in between, but the core algorithm is still nearly the same as 30 years ago. And now it is simulated in a thread, the simulation, to make it more flexible, but it has a very long tradition, this program. What can we use this for? Well, this is a processing structure here, if you draw it on the screen. And what we can derive from this model are two important parameters which you can use for diagnostical purposes. One of them is the secretory gland of the thyroid gland, the secretory capacity of the thyroid gland. This is the maximum amount of thyroxine the thyroid can produce in 1 second under stimulated condition, GT or SPINA GT for structure parameter in inference approach. This is the abbreviation for SPINA, our method. And we can also, yes, this is a derivation of GT, the equation. We have defined reference ranges for this, and we have made extensive clinical evaluation of these parameters with more than 10,000 subjects to get reliable reference ranges and to get information how this can be translated to clinical practice. And another structure parameter we can calculate, it is sometimes too fast here, is a GD or spinal GD. That is a total activity of deiodeinases. These are enzymes which convert the thyroid hormone T4 to the more active thyroid hormone T3. And we can also calculate this from plasma concentrations in steady state with this equation. And we have also defined a reference range for this. And it is possible for a physician to calculate these parameters very easily with software Spina-Tur, which we have developed. And the physician can enter the values for 3 hormones, TSH, T4, and T3. Can also select units of measurements and several methods of determination which modify the response, and then we click on calculate and get the results. It's very easy to use this software and can use in clinical practice. Of course, it is written in Pascal, and the difficulty doesn't lie in the calculation, but it lies in the many possibilities, in the many combinations which can be used for free and total hormones and several units of measurements and so on, which have to be addressed. So what are the benefits of this software? Well, we could show that the parameters which we calculate correlate with important physiological parameters. So we could show, for example, that spinal GD correlates to the conversion of T4 to T3 as determined with radioactive thyroid hormones. We also could demonstrate that the reliability, that is the repeatability of the parameters, is better than for measured parameters. So we use the same parameters. We measure 3 hormones, TSH, free T4, free T3, and we put them into the equations. And as a result, we get more reliable parameters than the originally measured parameters, the hormones. And we could show that the diagnostical performance in terms of sensitivity and specificity is higher than of the measured parameters. And so the number of papers is continually rising over the years, and today more working groups from all over the world are using it, and we ourselves are only contributing the minority of papers on this topic. We have also scientific benefits, because from mathematical modeling we could explain why TSH, for example, here over the time is produced in pulses, and so it is not a constant concentration, so we have this complex pattern over time. We can explain it from properties of the feedback loop with mathematical modeling and computer simulations. And we also developed a new part of the feedback loop. So we discovered a new part of the feedback loop which was previously unknown by mathematical modeling, and so we could show that TSH directly stimulates not only the production of T4, which we previously knew, but also of T3 from T4 in the thyroid gland. And this could only be found by computer simulations because the raw data don't provide this clearness to come to this conclusion. And of course, we can use it in teaching. This is a computer resource center in one of our hospitals where we use it for student education. So the next story is insulin glucose homeostasis and the development of diabetes. We already talked about this. And here we developed also a nonlinear mathematical model of this feedback loop. And these are the equations of the model. I'm a bit faster now. And we developed software to simulate this. Simula Beta, the software, is also written in Object Pascal, of course. And this is a program. I will also show it you in the demonstration in the afterwards, because it is a very complex implementation of the CyberUnits bricks class library. But as you see here, we can simulate the evolution of insulin and glucose over time. We can simulate some function tests like glucose tolerance tests. We can predict the equilibrium and many more things can be used. We have published this model in the journal Scientific Reports of the Nature Group, and what we could show here, for example, is that the feedback loop approaches always the same concentrations of insulin and glucose, irrespective of the beginning. This is what the feedback loop does, of course. We get constant steady state output, and here we simulated some clinical tests which we use. For example, the oral glucose tolerance test. At least in Germany, every pregnant woman is offered an oral glucose tolerance test to detect diabetes in pregnancy. I think in many other countries it is similar. And this oral glucose tolerance test, these are the reference ranges, these are the simulated values, so are well within the reference range, not only for the steady state values, but also for the dynamic results. And this is an intravenous glucose tolerance test, which is less commonly used, but very commonly in research, and also we get results within the reference ranges. But perhaps more importantly, we also can derive clinical parameters for this. For example, we can, from this model, derive the beta cell function, G beta, the secretory capacity of beta cells, and can calculate these. And we can derive a parameter for insulin sensitivity or insulin receptor gain to get an idea about insulin sensitivity or insulin resistance of the subject. And we could show that these parameters correlate with many physiological predictors of insulin glucose homeostasis, like fat content, like obesity markers, and many others. So we get significant correlations, which give us an idea that these parameters really measure what we want to measure, and they are better than, these are the new parameters, and they are better in the correlations than traditional parameters, which has previously been used based on linear models. And they also provide new insights, which we previously didn't have. This is a compilation of the enhanced data sets, a very large population-based study in the United States. And what we see here are the green dots are healthy volunteers, and we see here insulin sensitivity, and here we see beta cell function. And we see if insulin sensitivity goes down, is worse, and the beta cell function is compensatorily increased. So the subjects have better beta cell function, and so they can compensate for insulin resistance. But this doesn't work anymore for subjects with diabetes and pre-diabetes. These are the red and orange dots here. So they may have a normal beta cell function, but for the amount of insulin sensitivity, it is not enough. So we learn a lot about the physiological function by these models. So, of course, the story goes on, and in the last part of my presentation, I will present you the ongoing research which we currently make here. One of these projects is for the thyroid function in critical illness. This is made by my doctoral student, Nina Sigma. And we know already that thyroid hormones are down-regulated in critical illness. Most persons who are treated on an intensive care ward or are critically ill have low concentrations of T3 and T4 and TSH as well. And this also predicts the survival. It's a study we made, and we could show in persons with trauma that a low set point of the feedback loop predicts poor survival. These again are parameters which are derived from our models, and this is an independent predictor of survival. And what we also know is that the pulsatile release of TSH and the upstream controlling hormone TRH is lost in critical illness. So normally we see this pattern over time, and in a severely ill subject, we have not only a low concentration, but also the pulses are lost. But we don't understand this up to now. And this is for TRH, the same pattern. And now we have developed a new theory. And if we looked at how these central hormones are controlled by the brain stem. This is the hypothalamus, this is the pituitary gland, these are the critical subjects in the brain stem which control the production of these hormones. And we see that the production of TRH is controlled by many afferent signals like stress hormones, like nutritional signals, like many other hormones which control this. And also stress signaling plays a major role. This is psychological stress here, modulated via the amygdala and other stress centers, which stimulate the release of TRH. And now our idea is that we have now the idea is that you don't see this luckily. Now the idea is that we have a combination of positive and negative feedback loops, which gives rise to the oscillatory behavior of the hypothalamus. And here we have negative feedback loops, TRH, these are the purple lines here, inhibits its own secretion, and it's only also inhibited by thyroid hormones. So we had short and long feedback loops which inhibit it, so negative feedback loops which tend to attain a constant level. But we have also positive feedback loops in the system. Okay, now it reacts. We have also positive feedback loops over the stress system, where TRH stimulates some stress hormones, which again stimulate the secretion of TRH. And this combination, this is our theory, could explain the evolution of pulsatile oscillatory behavior. So we have this processing structure, and we have here the local TRH concentration. We have here the amplification of the voltage ratio in the neuronal cells which produce TRH. Then we have here the weighted electrical potential. We have here the gain of TRH release. This is here this G2. We have here the gain of the local TRH for the feedback path. And we have here the gain of catecholaminergic neurons, which then produces this catecholaminergic input by stress hormones. So we have here a negative feedback loop. This is a classical Maimon-Cody loop. So these are the TRH producing neurons where this takes place. They produce TRH, and this again inhibits its own secretion. But we have also positive feedback loop over the limbic system, the stress systems, and now we tried to simulate this. And to show you this, I now leave the presentation and this is a program here. And so we can simulate this system here with some standard values. Okay, thank you. And so we can see the evolution of time. We see here that we had oscillatory behavior with traits, but if we increase the value of G2, this was a gain of the TRH producing neurons to, for example, 20, and simulate this, then you can see constant oscillations here. So it depends on this, but also it depends on the behavior of other variables. And we can systematically analyze this by this bifurcation plot. And for this, we make many simulations of the system. I show you this in the source code, how we do this. It's written in free Pascal with Lazarus, and the problem is I can't see it on this screen, but I will try. Okay, it's difficult here for me to show you this, and I'm not sure if we can read it here. Bifurcation. What we do in principle is that we make multiple simulations of the hypothalamus. We make 50 simulations of the hypothalamus, and then to allow the system to settle, and then we make another 7 simulations of the hypothalamus, and then we record the values for the TRH and try to plot them. And what we can see then is that these we get a bifurcation here, which explains the oscillatory behavior. But this position depends on several variables, G1, G2, G3, and so the more important step is to make a bivariable plot to see which combination of G1 and G2 or G3 and G2 produces oscillatory behavior. And to simulate this, we have made a very complex algorithm. I think I can't show you it here now to the restrictions here, but what this algorithm does is that it it uses this coordinate system from 0 to 100, so we have 10,000 points here in this two-dimensional field, and for every one of these 10,000 points, sorry, I don't understand you. So, okay, yes, then I understand you. And for every one of these 10,000 points, it simulates the hypothalamus, and it makes the first 50 simulations for settling, and then 128 additional simulations to get time series over time. And what we then make in the next step is to make Fourier transformations of these time series with an FFT algorithm to detect if there are oscillations or if this is a constant behavior. So in summary, for this simulation, we had to make 1.78 million simulations of the hypothalamus and 10,000 fast Fourier transforms to get this picture. And now I'll show you the results of the simulations. We made a resolution of 2 a bit higher, and you see it's a very fast computer with an M2 processor, and you see here now, what is green is oscillatory behavior, and dark red, thank you. And dark red is the constant behavior of the feedback loop. So this combination delivers us insights about the physiology of the system. And you see this is very demanding for a computer, and this very fast computer needs about a second for this. And if we have a higher resolution here, then it takes much longer time. And let's simulate this while I talk. But this is the reason why we need a fast programming language. So it was a scripting language like R or Python and interpreted language. We will have we will need perhaps a day or so to make these simulations. And so with Pascal, which creates fast machine code, which is optimized for the processor, it is fast. So let's go back to the presentation. Okay, it works again. I showed you this already and the simulation results. This is one of our projects. The next project is we want to understand the translation from the molecular level to the level of the whole organism. And we have developed a very good understanding in biomedicine for molecular mechanisms over the last 150 years. And we know a lot about enzymes, about genes, about other molecular relationships. And we know a lot about the whole organism on a clinical level. But what is difficult is the translation, is the scale between these two levels. And it is up to now nearly impossible to get responses about this. But we can now, with a new model, we can partly solve this conundrum. And let's go back to the Maimno-Cody feedback loop, which we already learned about. And let's look at this Michaelis-Menten kinetics here on the right. This derives from these chemical reactions, which I showed you already. And what is important is that we can express these two variables, G and D, in terms of these rate constants of the chemical reaction. And in order to simulate this, we use the Gillespie algorithm. This is an algorithm which was developed in 1967 by then Gillespie for the American military. And with this algorithm, the statistical simulation algorithm, and with this algorithm, we can explain the development of a chemical system. And for this system, let's assume we have here an enzyme and then a substrate, and again the rate constants for the enzyme substrate complex, and finally the enzyme and the product. And the enzyme and the substrate are converted with the rate constant K1 to the enzyme substrate complex, and this dissociates again either to the starting substances with a rate constant K minus 1, or to the enzyme and the product with a rate constant K2. And at the beginning, let's have 5,000 molecules of the enzyme, 1,000 molecules of the enzyme, 5,000 of the substrate, and 150 of the enzyme substrate complex, and no product at all at time 0. And then the idea of the Gillespie algorithm is to generate two random numbers and use these random numbers for two decisions. One decision, when will the next reaction take place, after how many milliseconds? And the second decision is, which of these reactions will occur? And for the second decision, we need information about the propensity, the basic probability by which this reaction will occur. So the propensity for this reaction is the product of these two concentrations times this rate constant. This delivers the propensity for the reaction. We have to account for this and use a random number together with the propensity to decide which reaction will occur. So this is the first step. We have these amounts and 0 milliseconds. Then in the next step, yes, I explained this already. Then in the next step, let's select this reaction here, the K minus 1 reaction. This means that the EA is degraded to E plus A. So we get one molecule less from the EA complex, one molecule more for the substrate, and one molecule more for the enzyme. And then let's take 5 milliseconds for the next step to occur. The next step may be this direction here with K1. Then EA already rises by 1, and the other two species decrease by 1. And then the next time may be 13 milliseconds, and then the algorithm may select this reaction to occur. Then EA goes down to 149, and we have the first product created. This is the idea of the Gillespie algorithm. And we have implemented it in Pascal here, and I try to explain it to you. Here we generate the two random variables, which we use later. Here this is a species vector, which is used with an exponent matrix to produce the propensity for the reaction and then the probability of the reaction. And here we use the time of the next reaction, so we need the random variable 1, and to decide when the next reaction will occur. And here with these lines, we select the reaction using the propensity and the random number to select the reaction to occur. This is a very demanding algorithm which uses a lot of computation power, and this is another reason why we need a fast programming language. This is a program we have written for this, and we can enter here the constants in this matrix for the rates. We have here the rate constants, and we have here the species. And then in the first step, the program delivers us a stoichiometry matrix and the reactions which will take place. And Here we have simulated it over 1 second system, and you see that the substrate goes down by the enzymatic process, and the product is produced by the enzymatic process. And the enzyme stays nearly constant. So how can we use this to translate between the levels, the molecular levels, and the whole organism level? So we have again simulated this Mann-Marconi loop here, and we get these equilibrium values of 5 for this variable x, and 5.15 for this variable u, and 5.077 for the most important, the control variable y of t. And now let's translate this to molecular relationships, and for this we divide by, we multiply by 1000, because we want to not address concentration but single molecules, so we have multiplied it by 1000. This is 5150, that's 5150 here for the substrate and the enzyme substrate complex, and then we can simulate this with the software, and what we get from this slope here is 5080 molecules per second, which are formed of the product. And to translate this back to the behavior of the whole feedback loop, we have to divide again by 1000, and then we get 5.08. No, I don't want to shut down the computer. Sorry. Where is my mouse? It is here. So where we were here. So I will skip these. You already saw this. So we get 5080 molecules per second, which is after division by 1000, 5.08 about. This is nearly the same like this 5 here, which we 5.08, which we simulated for the whole system. So this is an example. We have a MIME element, and I already told you that we can express these two variables in form of rate constants, and though we can get 3 variables A, B, and Z from these rate constants to solve for the equilibrium behavior of the whole system, and so we get here y of t in terms of k minus 1 or k1, and so we can translate from molecular properties like rate constants here to the behavior of the whole feedback loop. So this is the end of my journey. You see, this is, was a journey of 30 years of research, and with the help of advanced computer programming and fast software, we can we can today solve a lot of open questions which help for clinical decision making, but which also improve our understanding of the basic physiology. Thank you for attention.